So we are still in the BMI space because we will have Alexander Bartnik, former grad student in SUNY Buffalo, and now member of the Buffalo Neuroimaging Analysis Center. And we are very happy to have him here. So let me switch to the slides.
Okay. All right. Can you see now?
Yes.
Okay. Sorry about that. Thanks for bringing that up. Okay. So this was what for those of you who didn't see it before, this is the MRI scanner. This is an MRI image data set. The important thing that I want to stress about MRI is you can acquire different looking MR images with different contrasts, and that will determine what you can actually do with your image. You can acquire them by tuning the way that you use the scanner. So those we'll call our acquisition parameters or acquisition methods. And so those are ways of generating different kinds of contrast in the image. An example is this kind of gradient that you see here. TE stands for echo time, TR stands for repetition time, but jargon. But the point I want to stress is that as you adjust the parameters that you enter in at the scanner, you end up getting different looking images as a result. So with neuroimaging, the goal is to take your imaging data and turn that into information. So you do things like pre-processing, feature extraction, pattern recognition. You can do some deep learning approaches now that's been getting pretty sophisticated over the past couple of years. You can make predictions about clinical outcomes from imaging data now. Like I said, this all comes from your ability to acquire different kinds of imaging data with different kinds of contrasts. And these are just some examples of things you can do with MRI. So for example, in my lab, we'll automatically derive things like volumes of structures within the brain, connectivity between brain regions, looking at focal lesions. But like I mentioned earlier, I mostly work with MS, so we do a lot of work with identifying lesions in MS. One of the most important things to keep in mind with any biomedical imaging data is that it almost always conforms to the DICOM standard. So it's the ISO-recognized digital format for biomedical imaging. What DICOM really does is it sets out the way that you acquire your imaging data and the way that it is reported in the file headers. So every biomedical imaging scan that you will look at, in the headers you'll have tags that are always consistent with what they mean. For the most part, I'll go into some reasons why that's not the case always. But they'll tell you things like when the scan was acquired, patient name, age, and any other parameters that you use. That's always encoded into the DICOM headers. Taking that one step further, there's recently in the realm of neuroimaging been the push for what they call BIDS, or the brain image data structure. And this is really just you can think of it as a standard vocabulary for how you call your imaging data as you store it in a file system. So it kind of sits one step ahead of DICOM. It takes a lot of the information that you get from the DICOM headers and then just puts that into different file names. So this is great for encouraging reproducible data in the neuroimaging world, but it's a huge pain to go from DICOM to BIDS. It's all in the file names. There's a lot of string processing, and the DICOM stuff isn't really all that consistent in the first place. But with all that in mind, we have all of these ways of collecting all this data about the human brain. So what can you do with it? And that's kind of limited because, like I mentioned, different kinds of things that you'd want to do with MRI really depends on the way that you acquire it and the different types of MRI that you're working with. There's not a lot of standards for the data itself beyond just DICOM header tags, meaning that you need to manually curate a large amount of data, mostly by yourself. There's not really good ways of sharing data just beyond copying files from one computer to another. And there's a lot of training and expertise that goes into working with these specialized tools. And so that's where Ontology comes in. And so a lot of our work on MRIO was motivated by trying to address most of those limitations. So MRI is pretty good ontology is great for capturing the breadth of neuroimaging expertise. So things that I go and do on the day-to-day to my lab that isn't really extendable to people who haven't been doing this for years like I have. It's helpful for automating the classification of MRI acquisition types and deciding what kinds of analyses that you would do on your MRI data and how you can organize that after the fact. So now I'll spend the rest of the time talking about the MRI ontology and some of the ways that I can use that with real-world data. So MRIO was created to address the need for a common language in MRI. It provides well-reasoned classes and logical axioms for MRI acquisition and different kinds of analysis software that you can use with your MRI data. It helps to standardize the organization of the data itself as well as the analyses. We also provide some tools and some queries for automating some of the steps of the neuroimaging research process. And it was constructed in accordance to OboFoundry principles. And as Alex Steele mentioned earlier, we've worked a number of times to contribute some of our higher level terms and classes to OB. So when we talk about MRIO, I like to think of it as both a domain ontology and an application ontology, in that it provides a lot of standards for the actual domain itself, a lot of the higher level knowledge that kind of goes into how you work with your MRI data. And I also use it a lot with real world data. So I try to focus a lot on the practical benefits of MRIO. And so I can't take all of the credit for MRIO. A lot of people have been involved with this process for a number of years, even before I started working on it. It was first presented at ICBO in 2019 by Dr. Lucas Serra, who was Alex Steele's previous PhD student, in collaboration with Alex Steele and Mike Dwyer, who was my PI for my PhD. And so a lot of the basic design decisions for MRIO came from Lucas Serra. That includes using BFO as a base and building off of OB and IAO. And one of the central things that come out of our work on MRIO was this image dataset class. This is something that I presented on at ICBO in 2022. So I think it was IAO had an image class that was the specified output for an MRI assay that was already in OB. And we looked at that and thought, this doesn't really apply to MRI data all that well. MRI data is three-dimensional. If you think back to one of the first slides that I showed, there was the three views of the same brain, just that with different cross sections coming from different angles. And that's because your MRI data isn't a two-dimensional image. It's really a set of data in 3 dimensions that is reconstructed in a way that you can look at in those different planes. So we ended up creating this image dataset class, which we use mostly for MRI and MRIO, but like I mentioned with a lot of the DICOM stuff, this also applies to really any other biomedical imaging modality, and that's something that we've talked about with the recent grant we've been working on for IOMBA with Carl Hummer from MGH in applying a lot of this to imaging modalities even beyond MRI. This is a schematic of how the MRI acquisition process is represented in MRIO. So at the center, we have the MRI assay, and this was something that already existed in OB, but we added a few axioms to fit more of our paradigm. But as I mentioned earlier, there's you have your MRI scanner. In OB, they call that your NMR instrument. And so that's where your giant magnet sits that puts your protons in alignment. You key in your RF pulses or your pulse sequence protocol at the scanner. So that's part of the planned process for the MRI assay. And you also have your MRI participant serving as an evaluant role. And so that all fits together to produce this raw magnetic image data set. And I mentioned earlier, there's the whole K-space Fourier transform. So that's another step after this, but we're saying, okay, this just outputs the raw image data set. What we can do after that is you reconstruct that to your reconstructed MRI data set. So that's going from your K-space through your Fourier transform. Now you have a reconstructed image data set. That can be passed on to an MRI data set analysis, which is a child of the data transformation class from OBI. And so these are different things you can do with MRI data, such as lesion analyses, volumetric analyses, segmentation using a deep learning model. And these are all children of this MRI image data set class that all output some sort of information content entity. So you start with your person in a scanner. They go through the whole process of acquiring the image with the pulse sequence protocols. You get your reconstructed MRI data set out of that. You do your analysis, and then you get some information content entity derived from all of that. And so whenever we work with our neuroimaging data in the real world, we're mostly concerned with our ICEs that we get out of these analyses. And so one of the main things that we ended up using MRIO for, one of the undergrads that worked under me, Mackenzie Smith, who was also a student of Alex Steele's, wrote a Sparkle query to help people just type in what kinds of MRI data that they have. So for example, T1 weighted and T2 flare are just different kinds of MRI data. They're just different ways of acquiring an image of the same brain, essentially, but you can do different things with them. So you just type in the name of the sequence that you have, and MRIO will, or it'll find the analyses in MRIO that you can do with these kinds of imaging data. Additionally, we also integrate with the DICOM standard and BIDS I mentioned earlier. It is a pain to go from DICOM to BIDS. On the left, this is what files of DICOM images would look like on your computer. You want to go from these random strings of numbers and letters to your nice, organized, consistently named data. It is a huge pain to actually do it in practice. MRIO has terms that are mapped between the two that help with that. And I'm going to wrap up with some examples of how I used it in a central neuroinformatics platform. And so this was the bulk of my thesis work. This is a big picture overview of it. So it was mostly using this web application called XNet, which is an open source NIH supported database system for neuroimaging data. It's meant specifically to work with DICOM data. I'll focus on really the right side of this figure. That's where the MRI ontology really fit in. So I'll start with the automated analysis portion of it first. So the way that the pipeline or the platform worked is you send in your unsorted DICOMs. You classify them according to the acquisition parameters. You assign the analysis to them, and then you annotate the results of those analyses and expose it in a way that people are able to easily query. We also extended the relational data that was already in XNet by adding some additional clinical data types. These actually came from things like Uberon, Mondo. I think the cell ontology might have shown up in here as well. But a lot of clinical data wasn't in XNet because it's imaging focused, so we were able to just add that and extend the queries that we can do that way. And so this is kind of an example of how we would do this. We used a software called OnTop that maps between ontology terms and relational data. In XNet, it's a PostgreSQL database. So what we're able to do is put in the middle of the database and the ontology this OnTop program, and through that we can submit Sparkle queries. So as an example of what this one up here looks like, we say, okay, find me everything about the thalamus in our XNet database. And because everything is mapped nicely to the ontology, we can get some real world data out of this. And Sparkle, I don't know how all of you feel here, but in my neuro part of the world, no one knows what Sparkle is, and no one wants to learn what Sparkle is. So we developed a front end for pre-formatting the queries. So, for example, to do the same query that we saw above, we just have a nice little drop-down menu that you click on and say which ROI you want information out of, ROI meaning region of interest, and it would return all of the data in the database, either in graphical format or as tabular data that you can download and do further statistics with. We also built in some other ways of playing around with the data that was all queried using Sparkle and OnTop. I mentioned earlier, I do a lot of work with MS, so a lot of this is focused on looking at clinical outcomes in MS. So this is all data that you would be interested in if you wanted to do MS research. And this is more of another higher level overview of how it all kind of fits into the platform. And then finally, we also used MRIO as the glossary for the statistics portal for the platform. So anyone who wanted to know any little bit of data that you would derive from the platform, there's a nice link that you can click that will take you to the definition for it in the ontology, as well as some of the other related terms. So for example, if you were looking at lesion data in the platform and you don't necessarily know what salient central lesion volume means, you can click on it, and we have a nice link to the paper where this data was first introduced, and as well as a full definition of it. So in conclusion, MRI is a very versatile tool. We're continually seeing new applications of it to both the clinical and the research settings. So there's a substantial opportunity to apply bioinformatics methods to richly mine, identify, and interpret imaging biomarkers. But there's a great need for translationally viable quantitative imaging markers. And so Ontology helps bridge this gap by providing a means of better organizing and annotating imaging data, integrating them with clinical data, and sharing across institutions. And are there any questions?
Well, your pre-made queries for people returning the data, was it just based on brain regions, based on what all the
Yeah, so it was a mixture of brain regions and clinical and demographic data. Go back to, let's see. Okay, yeah, this is a good example. So here, really, all the user submits is a unique identifier for some time point. So in this case, the time point for this scan was EX, was that 56423, and so you would type that in and you specify whether or not you want to compare it to the disease group that this person was in, or if you want to compare them to normal controls or age. So there's a lot of demographic stuff that came from things like Mondo that was tied into the database through OnTop that way. And so things like the source of the data, demographic, age, sex, disease group, things like that, and as well as the results of the analyses kind of came out. So, for example, lateral ventricle volume is a metric that we automatically derive. Likewise with medulla oblongata volume, all these other ones that you see here. So, I mean, it all ended up being a little more complex than just the find me everything about the thalamus, which I think it is kind of cool that you can have a simple query that pulls out that much data. But there is a lot of depth that you could get through with these queries. So the idea was to provide something that was easier for people to use that also had the benefits of using richly annotated data.
Did you
Yeah, so on top, it gives that to you for free. It just exposes the Sparkle endpoint. So that is open technically. It's just not advertised. But yes.
Do you get an opportunity to talk a little bit more about Spark?
Mhm.
Are you using mostly select queries, or can you do like construct query through the user interface or anything like that?
Not through the user interface. So I will say it's all select queries. I know OnTop is limited to how many features from Sparkle it supports. And I think it might not support that. I think it might just do like simple select things. Um, but I don't remember off the top of my head. It's been a number of years since I actually looked at what OnTop supports, just because I got this out of it and said, okay, that's enough.
Are
But
all of the so can you put all of the object properties into the user interface, or is it just like REF type?
I don't see why not. I think the only thing that would stop you is uh, how much you want to work in web dev, I guess. Uh, at that point, you're just kind of typing out HTML tags for it. But I don't see why you couldn't.
Yeah, sorry, I'm asking questions about that.
Mhm.
Nobody wants to write a Sparkle query, but everyone wants to use Sparkle.
Yeah,
So I think everyone's trying to figure out how to do that with like preset Sparkle queries on the back end.
yeah,
Leverage the graph in the way that versus inadequate train Sparkle.
yeah, yeah. I think there's a lot of utility in that, but yeah, you have to be good with the Sparkle first, and you have to have the time to actually translate it.
Right.
You don't want to let people put it out this purpose.
What's that?
You probably don't want to let people put it out this purpose.
No, yeah. I think
No insert.
yes. I was going to say I would make it as read only as possible. But yeah, but I think there probably is some utility to it. But, I don't know, maybe not necessarily in this case.
Well, you know, Steve mentioned they're continuing to work on MRI, we know. Big transition. Father. Yeah, very talented. Computer science student work, past summer from related to functional MRI and MRI and hopefully some of that road coach as well.
Mhm.
It's a continuing project.
If there are other questions, we can have a 5-minute break and then we will get going with the planning session, which
I think they're going to want to leave this room.
okay. Okay,
Maybe they'll give us the people.
okay.
I don't think we should have a break. Just in case we're thrown out.
Exactly. That will be the major break. But thank you, Alex.
Thank you.
Thank you for listening from abroad, wherever you are.